Here we go with section 2.5. We are still focusing on our functions, our family of functions, in fact. We're going to fill out those families of functions by first reviewing the parent function and then moving on to talking about how to transform that parent function into any other graph function of that same type. So here's what I want you guys to do. I want you to, without your parent function sheet, I want you to fill in as much of this as you can. You're going to name the functions. If you can label them as even, odd, or neither, do that. Tell me what kind of symmetry that means, and give domain and range for each of these 6 functions. So pause the video, fill in everything you can, and then restart and see how you did. Alright, I'm going to kind of define my space here. We're going to go through. Hopefully you got most of these without having to look back at your parent function page. If you did look back, at least you know what you don't know and what you need to practice on. Because you need to have memorized each of these shapes and know what type of function each one is. The key, the clue for the function, a good clue is in the equation, the function itself. And then you need to be practicing matching that equation with the shape of the graph. Okay, so let's do domain and range first. And then now that we've got our titles on, we're going to do domain and range, and then we will go through and do symmetry. So we've named our parent functions, domain and range. I'm going to start with linear. Linear goes forever in both directions, up, down, left, right. So the domain and range for my linear function is all real numbers, negative infinity to positive infinity. This is true for every linear function except a constant function and a vertical line. A vertical line has only one value for the domain. Horizontal line, the constant function, has only one value for the range. My cubic function also has domain and range of all real numbers, and that's not supposed to be a fancy tail in the middle of my infinity sign. I just do that, not on purpose. And the cube root function, domain and range, are all real numbers. Negative infinity to positive infinity, always list those lists to greatest. Our absolute value and quadratic functions have domains that are all real numbers, but they have a limit to the range. So my domain is all real numbers for both of these functions. And once it is all real numbers, it's always all real numbers. There's no way to change that. However, when we have a limit, like both of these, the parents have a limit on the range of 0, so they have a minimum of 0 to positive infinity for their ranges. Anytime you have a limit, that limit can change. If I shift my function up or down, that limit changes with it. If I flipped it over the x-axis, it would be that limit would become an upper limit instead of a lower limit. Okay, so we got those two, we've got these 3 done. We're left with our square root function. Our square root function has a minimum value for both domain and range. The domain and the range for my square root function have a lower limit of 0. Okay, now the last thing we're going to put together for these functions is to talk about it as even, odd, or neither. And we did that when we filled out our parent function page back in 2.1, I think, 2.2. Even functions are symmetric about the y-axis. Right here, we've got 2 even functions. They have y-axis symmetry. That y-axis symmetry means I can fold it on the y-axis and the sides are going to match. An even function, remember algebraically, my test is to plug in a negative x, and if nothing changes, it's an even function. Odd functions, when I plug in that negative x, the opposite value happens. Everything changes. So my linear function, my cubic function, and my cube root function are all odd functions. Odd functions are symmetric about the origin. They have origin symmetry. And you pair those O's together so you can help remember origin symmetry. Symmetry. And then mathematically, instead of plugging in a negative x and nothing changes, if I plug in a negative x and it's odd, everything changes sign so that I get out the opposite of what I started with. My square root function with my two limits, limit on domain, limit on the range, it doesn't pass either. It does not pass the symmetry test as even or as odd. So we label it as neither even nor odd, and we say that it is not predictable symmetry. I can have a function, this one does not have symmetry at all, but I can have functions that are neither even nor odd but do have symmetry. It's just not around the origin or the y-axis. Okay, so that was our kind of quick review. Let's move on to our transformations of functions. Remember, these are my parent functions. They're the most basic of each type. But I can take, for example, this absolute value v, I can shift it left or right, up or down. I can flip it upside down. I can stretch it out so it gets skinnier. I can squish it together so it opens wider. It's still an absolute value v. I haven't changed what type of function it is. My transformations come in rigid and non-rigid versions. If I have a rigid transformation, it retains the exact shape. So like I have this particular V. It's not going to open wider or narrower, get skinnier or fatter. It just moves left, right, up, down, flips over. Those are rigid transformations. My rigid transformations are horizontal, that's left, right, vertical shifts, horizontal or vertical shifts, and reflections over either the x or y axis. Those are rigid. My non-rigid transformations are going to be where I take it and I stretch it up so it gets skinnier when I stretch it, or I squish it and it opens up wide. It's called a shrink or a compression. But those are non-rigid. It's still a V, but it doesn't retain the shape. It changes the shape. Still a V, but it's not the same sized V as it was. That's my my stretch or shrink, which can really be better termed a compression. Okay, we can do our non-rigid transformation, our stretch and our shrink. I can do it vertically, think about pulling that up and down, or I could think about stretching it horizontally or squishing it back together horizontally. We're going to focus on vertical non-rigid transformations, vertical stretches and compressions in this course. If you go on and end up doing some trig functions, we focus a little bit more on horizontal stretches and shrinks. Okay, general pattern of transformations. This is going to hold true for every type of function you do this semester, all the way up through those trig functions. Any type of functions, you follow the same pattern of transformation. So I've named my function f of x. It could be named anything, but that's my function name I picked. This coefficient out in front, that is that non-rigid transformation, that stretch or shrink compression. It's a stretch or shrink. I can also call my shrink a compression. If this number out front is a whole number, 1, 2, 3, 4, 5, 6, 1.2, 2.2, anything greater than 1, it's going to be a stretch. If it is a proper fraction, something less than 1. So greater than 1, it's a stretch. Less than 1, it's a shrink. Doesn't matter if it's positive or negative, okay? That greater or less than 1 is a stretch or a shrink. Inside attached to the x is the horizontal axis, right? So attached to the x is going to be my horizontal shift. H for horizontal. Horizontal shift. Now, I've got a little box up here. This could be a square, square root, cube root, absolute value bars, whatever is my function. That is inside the attached to the x. That's my horizontal shift. Now, I want to point out to you this starts out as x minus. So if it ends up as x minus 4, I plugged in a positive 4. That's going to take me 4 units to the right because I actually plugged in a positive 4. That x minus started out there. Okay, enough about that right now. Next, we've got our plus k tacked on at the end. K, H is for horizontal, K is the other direction. So this is my vertical shift. It's going to take me up or down, and it goes the way I expect it to go because it's just a plus. I don't have to worry about that being plus, minus, anything else. Now, I can also have a reflection. Reflections show up if I have a negative out in front. That would cause me to reflect across the x-axis. If I had a negative right here in front of the x inside the parentheses, that's going to be reflection over the y-axis. So negatives make me reflect. That negative can either be out in front and it's reflection over the x-axis, or inside attached to the x, and that causes it to reflect across the y-axis. Make sure you've got this clear and easy to see. This is going to be your pattern of transformations that you are going to use all semester and on into pre-cal and calculus if you stay in math that far. Now, you might have a bunch of transformations to do. Your function may include all of those bits and pieces. And if that's the case, you need to know what order you want to apply them in. If there are multiple transformations, you're going to start by thinking of moving horizontally, horizontal shift. That's that H inside the parentheses. And then you think about applying any stretch or shrink, stretch or compression that you need to do. That's that value A out front, our non-rigid transformation. And then I would reflect across whichever axis I need to reflect it across. That's any negative I might have applied somewhere. And finally, I think about applying a vertical shift up, down, and that's controlled by the value K, whatever K might be. Now remember, you've got this pattern of transformation set beside you so that you can be looking at it while we do our practice transformations. Okay, so pay attention when I give you assignments. I often want you to graph the parent function and the transformed function on the same set of axes. So if I look at f, g, and h of x, I see they are all the same type of function. If you need to, look at your parent function page, but hopefully you recognize that this is our quadratic function. So I know in my head immediately that the shape of my graph is going to be a parabola. So let's do that. Let's do my parent function first. Parent function x squared is a parabola that sits at the origin. 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4. My parent parabola opens up just this much. There is my parent f of x. So now let's do g of x. G of x is a transformation on our quadratic function. And the transformation I've been given is right here. And if I look at my transformation pattern, I see that that started as x minus, and then I plugged something in so that I ended up with plus 3. Well, to get a plus 3 there, I had to have plugged in a negative 3 because minus a negative is x plus 3, which means I'm shifting 3 units to the left because I had to plug in a negative to get that to show up as x plus 3. That's my transformation. My transformation is that I'm going to shift left 3 units. My vertex, for my parent function, my vertex was at 0, 0 at the origin. My new vertex is going to move over, so my new vertex is going to be at negative 3, 0. This is a rigid transformation, so I want to strive to make sure that I keep my parabola exactly the same, just shifted over. I'm not going to measure out points here, but I'm going to do my best to mirror and have the same size opening for g of x. Okay? And then my third transformation, h of x, I've got my shift left 3 units, and then I've tacked on this minus 4. Well, if I look at my pattern of transformations, that's my vertical shift. It goes the way I expect it to because it starts out as plus. So that minus 4 tells me I'm going down 4 units. Both of these are rigid transformations. My vertex started at 0, 0. I shifted left 3 and down 4. So my new vertex is at negative 3, negative 4. Now I want to point out that those values, hk, those values give me my vertex. If h and k are missing, my vertex is at 0, 0. Here I have a value for h, so I've changed that x coordinate to the h coordinate. Here I have a value for h and for k. So my vertex for my parabola, or for any shape, is going to be found by finding those values hk. Alright, so my vertex goes to the left 3, down 4, and it's rigid, so it should look like the other 2 parabolas that are already on my graph. Okay, so there's my parent function and 2 transformed functions on the same set of axes. Let's look at the next one. Alright, we have a new parent function. My new parent function, use your parent function page if you need to. My new parent function is absolute value. The vertex for the parent is at 0, 0. Absolute value cuts right through 1, 1, 2, 2, 3, 3. Just like that. That's my parent function, f of x. My first transformation, g of x. Which way am I going? Well, it's inside the absolute value bars attached to the x. It starts as x minus, so I plugged in a positive 5. So that's going to go 5 units to the right. That's a rigid transformation because I'm just shifting it over. My vertex now needs to move to 5, 0. Strive to keep it the same opening as it was. I didn't do a great job, but it's not awful. And then finally, h of x, that same 5 units right. And then I'm going to shift up 2 units. Both of these are rigid transformations and leaves me with a vertex at 5, 2. Rigid transformations, same opening as the other 2, as much as you can. So this one was h of x, this one was g of x. Alright, so parent function, 2 transformed functions in the same family, all the same shape, rigid transformations. I think about what the transformation is, whether it's rigid or non-rigid, and what the vertex is. Think about why this vertex is a positive 5. and this vertex was a -3. Think about what in my function causes that to happen. Now we're going to focus on reflections a little bit. It reflects across the x-axis when I have a negative out in front. So to get from my parent function to my transformed function, I have that negative out in front, not inside being squared, but out in front. So parent function, f of x equals x squared, right there. Transformed function, g of x, is a negative x squared. That negative out in front tells me that I am reflecting that parabola upside down over the x-axis. That is a rigid transformation. Did not move the vertex. The vertex is still at 0, 0. For this function, this is g of x. For this function, I have a minimum. My range goes from 0 to positive infinity. For g of x, my transformed function, I have a maximum. That's the highest point now. My range goes from negative infinity up to 0 and stops at 0. I have a maximum value instead of a minimum value. Domain is all real numbers. Once domain or range is all real numbers, it's always all real numbers. So that negative out front is what reflects something across the x-axis. Now let's think about what would cause a reflection across the y-axis. Now notice I changed my parent function because if I was working with my parabola and I reflected across the y-axis, would there be a change? There would not. It would look exactly the same. You wouldn't be able to tell it was reflected. That's because my quadratic function is even. So we have to pick something that's not an even function. I chose our square root function. My square root function is not an even function. My parent function f of x looks like this. It has a lower limit. My domain is from 0 to positive infinity. My range is also from 0 to positive infinity. G of x is my transformed function. To get it to reflect across the y-axis, I have a negative, but now that negative is attached to the x inside what the function type is. So it would be inside absolute value bars, inside being cubed, inside being squared. In this case, it's inside my square root. That negative inside attached to the x tells me I'm going to take this and I'm going to reflect it across the y-axis. This is still a rigid transformation. My vertex is going to stay at 0, 0. It's just that I go the other direction. And I do my best to make it the same so that this y-axis is a line of symmetry, and if I were to fold it, they were to match up. This is g of x. My domain is no longer starting at 0 going to positive infinity. My domain is now starting at negative infinity and going to 0 and stopping. That's the domain for my transformed function. The range is still 0 to positive infinity. The range hasn't changed. Notice that things that are all real numbers are always all real numbers. If you have a limit though, that limit can change depending on the transformation you do. If you're supposed to list transformations for me, you can't just say reflection. You have to tell me where we're reflecting it, across the x or the y. Okay. Vertical stretch or shrink. Remember, another name for a shrink is a compression. Some people that makes a lot more sense to. That's fine. I just make sure you recognize it either way. If you're doing a vertical stretch or shrink, you are going to multiply by that coefficient a. There's my coefficient. You're going to multiply by a if you're doing a vertical stretch or shrink. Down here, just remember I said we're focusing on the vertical stretches and shrinks. Horizontal stretch or shrink, instead of multiplying, you would divide by that coefficient a, okay? you're going to divide by that a, and the a goes inside underneath the function value. So if it's square root, squared, cubed, that gives me a horizontal stretch or shrink. Vertical stretch or shrink, it's outside. It's not in here being squared, it's out front. So whatever that value a is, if it's a whole number, and by whole number I mean the absolute value is greater than 1. It could be 2.2, 3.7, 12. If it is greater than 1, don't worry about positive, negative. That negative tells me about reflection, remember. We're just interested in the absolute value. If it's greater than 1, it's a stretch. If it is a fraction, if it is less than 1, it's a shrink or a compression. So let's just start with our parent function. Y equals x squared is our parent. Say that is our parent. Put our parent function on both sets of axes. There's our parent. If I want to stretch that, let's say I'm going to stretch it. I'm going to say g of x is 2 times x squared. This 2 is a whole number, it's greater than 1. It's going to be a stretch. That means my parabola goes up twice as fast. So instead of this opening, I think about pulling the ends apart and stretching them. 1 squared is 1, 2 squared is 4, 1 squared is 1 times 2. It goes up twice as fast. 2 squared is 4 times 2. That would be up here at 8. So my stretched parabola, g of x, gets skinnier. I think about pulling the ends and it gets skinnier. So let's say over here we've got h of x, and instead of a 2, we're going to do 1/2. Well, if a 2 made me shoot up faster and stretch out, this 1/2 is going to do the opposite of that. It's going to make me compress. Now think about taking it and squishing it. If I take my parabola and squish it, it's going to only go up half as fast, and it gets squished down, it gets wider. It's a shrink, a compression, and it gets wider. This one gets skinnier, narrower, that one gets wider. So 1 squared is 1 times 1/2 is only halfway as far. 2 squared is 4 times 1/2 just takes me to 2. So this g of x over here is parabola, but it's not rigid because it opens out wider. It gets wide faster. No, that didn't make sense. It stays wider. Let's just stop there. Okay. Horizontal stretch or shrink. I've got that coefficient inside the function, whatever's going on, square, square root, cube, whatever. Instead of multiplying by that coefficient, I divide, and it does the opposite thing. So where a whole number gave me a stretch here, a whole number gives me a shrink here. But again, we are going to focus on those vertical stretches and shrinks. You need to know what the horizontal does. You may see a question about it in my math lab, but for the most part, we're focusing in on verticals.